For decades now, we've been working with one main story about our universe. It's expanding, sure, but it's also speeding up. But what if the engine that's flooring the gas pedal isn't some extra mysterious ingredient at all? What if it's just built into the very fabric of nothingness itself? Okay, let's dive into this.
All right, here it is, the big question at the heart of this entire idea. What if dark energy, this mysterious force that we think makes up almost 70% of the entire cosmos, what if it doesn't actually exist? At least not as some separate energy field. What if we've just been looking at space-time itself the wrong way?
So the theory that's currently the champion, the one called the Lambda CDM model, tells us this. The universe is expanding, and some kind of repulsive energy, we call it dark energy, is pushing everything apart, faster and faster. It's kind of like an ingredient we have to add to our cosmic recipe just to make all the observations fit. The only problem? It's a complete mystery.
Okay, so now let's get into the alternative. This idea comes from physicist Gerald Welch, and it's called unified spacetime, or UST for short. And instead of adding a new energy source to the universe, UST basically says we need to fundamentally rethink what gravity and the vacuum of empty space are even doing. This quote right here, this is the whole thing in a nutshell. It really has two key parts. First, it's saying that the default, natural state of totally empty spacetime is to be repulsive. And second, that in crowded places, like right here in our galaxy, all the matter around us screens, or kind of hides this underlying repulsion. So let's break down that first piece. A de Sitter baseline. What does that mean? It means that if you could find a chunk of the universe with absolutely nothing in it, no matter, no radiation, nothing, it wouldn't just sit there being all flat and neutral. No, its natural tendency would be to expand. The repulsion isn't something added to space, it is the baseline nature of space.
Okay, so if that's true, why don't we feel this constant push all the time? Well, that's the second part of the puzzle, screening. The theory argues that the presence of matter, stars, planets, galaxies, the whole shebang, it creates an environment that basically suppresses or cancels out that baseline repulsion. So right here, inside our galaxy, gravity acts just the way we expect it to, because all this matter is screening us from that underlying cosmic push.
And this is where the idea gets, well, really elegant. It lets us think about cosmic acceleration in a totally new way. It's not a push, it's a relaxation. Let me show you what that means. I want you to picture a pendulum, right? When you hold it up high, it's got potential energy, but you don't need to add some new falling force to make it swing down. You just let it go and it naturally relaxes to its ground state, its lowest energy state at the bottom. UST is proposing that the universe is doing the exact same thing. As all the matter spreads out and the cosmos gets emptier and emptier, it's simply relaxing back to its natural repulsive baseline state. The acceleration isn't being driven by a new force, it's just the universe returning to normal. Now, to really get a handle on this concept, the theory uses this diagram called the UST quadrant map. What it does is it divides the entire universe into two basic regimes, and it's all based on one simple question. In any given spot, is matter's attraction winning or is the baseline's repulsion winning? The most important part of this map is that line going across the middle, the Tucker horizon. You can just think of it as the tipping point. Everything below that line is attractive space. These are dense regions where gravity is the undisputed champ. But everything above that line is repulsive space. That's the vast cosmic voids where that baseline repulsion takes over. The cosmic acceleration we see is just the universe spending more and more of its time in that top half, in the repulsive zone. Okay, so this is a really fascinating idea, right? But is it actually science? A theory is only useful if there's a way to test it, a way to prove it wrong. And this is where UST gets really compelling, because it proposes a very specific, falsifiable test.
So where would you even look for this effect? Well, you'd go to the emptiest places you can possibly find, the cosmic voids. These are these unimaginably huge regions of space with almost no matter in them. According to UST, this is exactly where the screening effect is at its weakest, and that baseline repulsion should be out in the open, clear as day.
The test itself involves using two different tools to look at the very same voids. The first is called CMB lensing, and it uses the faint afterglow of the Big Bang, the oldest light in the universe, as a kind of backlight. The second is galaxy lensing, which uses the light from much more recent galaxies. So you have two different ways of measuring how gravity is bending light around these empty voids. And then the test boils down to something that's actually pretty simple. It's a measurement called the ratio statistic, or just R. You literally just take the measurement you get from CMB lensing and you divide it by the measurement you get from galaxy lensing for the exact same set of cosmic voids. You're just asking, do these two different tools get the same answer when they look at the same thing?
And folks, this is where the rubber meets the road. The standard model and UST make completely different predictions here. In the standard view, both probes should pretty much agree with each other, so that ratio R shouldn't show any real pattern as you look at emptier and emptier voids. But UST, it predicts a very specific pattern. As the voids get deeper and emptier, the two probes will disagree more and more, and that ratio R will consistently go down. It's a clean, testable fork in the road. One has to be right and one has to be wrong.
And you know what makes this a really strong scientific proposal is that it's committed ahead of time to how it can be proven wrong. The theory is officially considered falsified if that ratio R shows no consistent decreasing pattern, or if any pattern we do find can be just explained away by some measurement errors. There's no wiggle room here.
So let's just imagine for a minute. We run the test, we look at the voids, and the data perfectly matches the prediction from unified space-time. What would that actually mean?
Well, if USD is correct, it's a huge deal. It would mean that dark energy isn't some mysterious substance we need to go out and find. It would mean that cosmic acceleration is actually a fundamental property of space-time itself, something that just emerges naturally as the universe gets emptier. We wouldn't be looking for something extra. We'd be realizing the true nature of what was there all along.
And that leaves us with this final, kind of mind-bending thought. This theory suggests that the most powerful engine of cosmic change isn't hiding in the hearts of stars or galaxies. It's in the vast, empty nothingness between them. So could it be that the most important defining feature of our universe isn't what it contains, but the true nature of its emptiness?